Welcome back to The Explainer. Today, we are jumping right into a totally fascinating mystery sitting at the absolute center of modern tech. We're talking about how artificial intelligence actually handles memory. Now, we often picture AI as this infinite sponge, right? Just endlessly soaking up the entire internet and keeping it filed away perfectly forever. But behind the scenes, the reality is actually drastically different. In fact, teaching a massive neural network a simple new trick can literally erase the entire foundation of what it learned yesterday. So settle in, because we are going to explore the cutting-edge architectures engineers are actively building to save AI from its own forgetfulness.
And it really starts with this stark contrast. AI systems simply do not remember the way we humans do. Human cognition naturally accumulates knowledge. You learn to ride a bike, and decades later, you still know how. You learn a second language, and it doesn't just magically make you forget how to speak your first one. Our brains brilliantly build on top of previous foundations. But machine memory? Well, it operates under completely different and, frankly, much more fragile rules.
So let's get right into Section 1, AI's hidden memory problem.
The absolute crucial takeaway here is that AI is not omniscient. It actually suffers from this severe symptom where learning new information actively erases what it already knew. Imagine you're reading a massive 1,000-page novel, and with every new page you turn, a page from a book you read last year just vanishes from your brain. Poof, gone. That is exactly what happens inside a standard neural network when it gets exposed to fresh data. The system actually has to overwrite its historical patterns just to make room for the new ones. Which brings us to Section 2, the catastrophic forgetting flaw.
And catastrophic is definitely the right word for it. Catastrophic forgetting is this definitive, abrupt reality in machine learning. It's the exact moment an AI's prior capabilities are entirely overwritten by new data. We aren't talking about a slow, gradual decay over time. No, it is a catastrophic overwrite. You train an AI to perfectly recognize dogs, and it's brilliant at it. Then you take that exact same model, teach it to recognize cats, and suddenly, it has completely forgotten what a dog looks like. This isn't just a tiny glitch. It's a fundamental, foundational flaw in how these models have historically been built.
Okay, moving on to Section 3, why more data fails.
You might be thinking, well, why not just brute force it? If it forgot the dogs, just mix the dogs and cats together and retrain the whole thing. And sure, that was the old approach, just pile on more training data from scratch. But as these models have grown massively in size, retraining everything from the ground up every single time you want to teach it one new fact, it's computationally impossible. It just breaks existing knowledge. So that limitation forced researchers to pivot to a totally new approach, creating dynamic architectures that actively preserve existing knowledge, striking a balance between continuous adaptation and long-term stability. Let's look at how they do that in Section 4, the continual learning arsenal. We are looking at a seriously cutting-edge toolkit here to fix this problem. First up, you have replay-based learning, which is exactly what it sounds like. Literally feeding the AI a quick review of past material while it learns new stuff. Then you've got these mathematical shields, regularization techniques like EWC, SI, and MAS that protect vital neural connections so they don't get accidentally overwritten. We also have parameter isolation using incredibly clever tools like adapters and LoRA to physically cordon off the old knowledge. Add in Retrieval-Augmented Generation, or RAG, dual memory architectures, knowledge distillation to pass wisdom from older models to newer ones, and Modular Mixture-of-Experts designs, and you have an absolutely brilliant set of workarounds to keep AI memory intact.
Now let's zoom in on one of those in Section 5, building dual memory AI. For the longest time, an AI's entire memory was jammed into its weights. Those internal mathematical connections inside the network. But modern dynamic AI systems don't do that anymore. They no longer rely solely on internal weights to store every single fact. The most effective systems today treat model weights as just one component of memory. Essentially, they are separating the thinking part of the AI from the storage part of the AI.
And here is how that dual memory framework comes together in 3 steps. Step 1. You have the foundation model weights. This is your core intelligence, the reasoning engine itself. Step 2. You introduce retrieval systems and external knowledge stores. So rather than cramming facts into the weights where they might be deleted later, the AI is taught to look up information from a perfectly preserved external database. Finally, Step 3 utilizes continuous evaluation pipelines to constantly double-check that the AI's fresh insights aren't secretly destroying its historical data. It's just a beautifully balanced ecosystem.
And finally, Section 6, the future of trustworthy AI. So why does all this dense architectural stuff actually matter to you and me? Well, it boils down to reliability. Trust depends not just on raw intelligence, but on the ability to learn without forgetting. Think about it. If we are going to let AI drive our cars, or manage our healthcare systems, or run our power grids, we absolutely cannot rely on it if a routine Tuesday software update might cause it to catastrophically forget the basic rules of the road or standard medical protocols. The evolution of true, dependable intelligence absolutely requires preserving history.
Which leaves us with this really provocative question to ponder. Can we ever build truly trustworthy AI if it cannot learn without forgetting? I think that perfectly encapsulates the entire catastrophic forgetting problem. Because as long as learning new things means destroying old knowledge, our reliance on these systems is always going to hit a ceiling. But as we've explored today with these incredible new dual memory architectures and parameter isolation techniques, the brightest minds in the field are already dismantling that ceiling, brick by brick. Keep that question in the back of your mind as you watch the tech landscape evolve. Thank you so much for joining me for this explainer, and I will see you on the next one.